and welcome to this episode of Miss Elmore's Algebra 2 class online, and Behavior and Finding Zeros, Polynomial Functions. What we're going to look at today is not actually finding the real zeros, but by the time that you finish watching this little video, you should have an idea of where the zeros are on the graph, and if you have real or imaginary zeros. End behavior is a review of what we've been doing. So these are the pictures that I showed you in class. We have the graph of x squared plus 2x minus 3. And remember that you might need to adjust your window when you're doing the graphing so that you can have a pretty graph that all fits into the window. This is an example of an even degree function with a positive coefficient, x squared plus 2x minus 3. Here's an example of an odd degree function with a positive leading coefficient, x cubed minus 6x squared plus x plus 5, the window, and what the function looks like. And an even degree function with a negative leading coefficient, negative 6x to the 6th, 5x to the 5th, plus 4x to the 4th, plus 3x to the 3rd, minus 2x squared, plus x plus 10. Window, and what the graph would look like. And finally, we have an odd degree with a negative leading coefficient. So we have x to the 5th plus 4x to the 4th minus 8x to the 3rd plus 7x squared minus 10x plus 15. Here is the window and what the graph looks like. Now we can describe in general, thinking about those graphs, what the end behavior of an even degree function would look like. That would be that the function would go to positive infinity as x goes to positive infinity, and even if the output tends towards negative, we'll see that the function actually goes in the same direction. So what we have here is that the function points up as x goes positive and as x goes negative. An even degree function with a negative leading coefficient, we actually have that the function will point down, or the function values go down and decrease as x goes to the negative and as x goes to the positive. And so regardless of your function, if it's even degrees, that means that your end behavior is going to be the same for either input of the function. So the end behavior for an even degree function with a negative leading coefficient, the function will tend towards negative infinity as x tends towards negative infinity, and the function tends towards negative infinity as x tends towards positive infinity. And for the odd degree function, we have basically that the end behavior would be that the function tends towards negative infinity as x tends towards negative infinity. The function tends towards positive infinity as x tends towards positive infinity. And for the odd degree function with a negative leading coefficient, the function is going to tend towards positive infinity as x tends towards negative infinity, and the function will tend towards positive infinity as x tends towards positive infinity. Oops, I messed that one up. Sorry, that means the function will tend towards negative infinity as x tends towards positive infinity. And so the function actually goes in opposite directions. So x is going negative x is going positive. Here, the picture, x is going in the negative, and x is going in the positive. So actually what it helps is for you to kind of graph these little pictures on the side here, or maybe a sample graph of f of x equals x, or f of x equals negative x, in order to keep this straight. Because even though I want you to memorize these, I don't want you to memorize that this is negative and that's positive for this type of situation. I want you to imagine what the graph at the end of the functions for very large input values would look like. Now, in class I had some of you guys figure out what the end behavior is for this. So what I would like you to do is pause the video, and I want you to write down what you think the end behavior would be, and then play the video and then check your answer with what I write. Pause now. You better be pausing and not just copying my answer right now. And the same thing for this one. Make sure you pause the video before you write, so that you can see the answer after you have written your response. So again, the whole point of end behavior is to base the end behavior on your simple functions. Now for the zeros. Okay, we're moving back to 0. The zeros are the inputs of the function that produce 0. That's why you can say that zeros are basically x-intercepts. But what I want you to think of instead of the x-intercepts every single time, think of x-intercepts in quotes, because what if there are no x-intercepts? Then your zeros are going to be imaginary. But if you think of the zeros as x-intercepts according to the definition of x-intercept, that they are the inputs of the function that produce 0, that's a really good way to think about what the zeros are and why they're called. Now, things to remember about zeros. Instead of looking at the end of the function or where it is going, we have to look at where the function value is 0. The number and the type of the real x-intercepts help you to determine the number of the real zeros. So there is an interaction between the real x-intercepts and the real zeros, but it doesn't mean that those are the only zeros that will be for the function in all functions. Also, non-real or imaginary zeros come in pairs. The reason why imaginary zeros come in pairs is because if you think back to a simple question of how to find the zeros of a function that has imaginary zeros. Now, a part of the function might have a quadratic where the square of some number is equal to a negative number. Now remember that if you square root this, you get This is just the process, not the concept. You get a positive and negative imaginary number. Now, the reason why you get a positive and negative imaginary number is because when you try to think about conceptually, you're asking what numbers have a square that is negative 9. Well, there's two numbers, because if you take negative 3i and you square it, you get negative 9. And if you get 3i and you square it, you get negative 9. Because I squared equals negative 1. Now, if we go back to our functions that we looked at before with the end behavior, the total number of zeros that this could have would be 2, because it's a degree of 2. So the total number of zeros that it could have would be 2. The total number of x-intercepts by the graph we can see is 2, and so then we can see that the number and type of the zeros would be 2 real. We can see that easily on the graph by your 2 numbers there. Now, if we looked at a cubic function, similarly, we can see that from the cubic function we can have up to 3 zeros. The total number of x-intercepts would be 3, and the number and type of the zeros would be 3 real, since these two match up, the total number of zeros and the total number of. Now, for an x to the 5th, we can have up to 5 zeros. The total number of intercepts is 1, which means that the number and type of zeros, we are going to have 1 real and 4 imaginary. Because you can think that if we have to have the same number of zeros in our function, that's total number of zeros, real and imaginary. The x-intercepts will determine the number of real. So x-intercepts mean the number of real zeros, and then the rest of the number that you have would determine the imaginary number, intercepts. The total number of zeros for this one could be 6. The total number of x-intercepts is 2, which means you have 2 real and 4 imaginary. Now, I want you to graph these functions on your own, and I want you to determine the maximum number of zeros, the number of x-intercepts, and finally decide the number and type of zeros. The answers are on the following slide. And so here are the answers to the questions on the previous slide. I suggest that you take notice of the windows that I have for each of the graphs, and also that if any of the zeros were imaginary, all of the imaginary zeros came in pairs. Think back to the quadratic or the square that's equal to a negative number. And here are the questions that I want you to email your responses to. I believe that I have given you the answers to these questions both in this lesson and also in class. Of course, if you have any questions, you can come and talk to me after spring break. But until then, please do your best to answer these questions with good responses, not jumbly, jurgly, unimaginative, uncreative, looking in the book, coming up with some random answer. I want good answers. I want good answers.